Now, we have looked at Stokes' theorem, the Green's theorem. We are now looking at the Gauss theorem, or Gauss divergence theorem. Gauss divergence theorem is actually a sequence of at least 3 theorems. And the best thing is to state it. There are textbooks have proofs of this thing. Like, as usual, I am not particularly interested in the proof. I'm interested in understanding what the theorem really states. And the divergence theorem is central to several other results in continuum mechanics. What do I mean by continuum mechanics? I mean your fluid mechanics, your heat transfer, your thermodynamics, your strength of materials, your elasticity, plasticity, viscoelasticity, all the things that engineers classified as continuum mechanics. Many of them are classified as continuum mechanics. It relates a volume integral of a field to the surface integral of the tensor product of the field and a unit normal. We present here a generalized form. I got this from a book by a man called Ogden, which states that for a tensor field psi, big psi here, the volume integral taking over the region of which is a section of the Euclidean point space. That volume integral, that is the grad of psi, integrated over the volume, is simply the same function circle times n, which is a tensor product of that function taking over the surface. So it is relating a volume integral to the surface integral. Remember that in Stokes' theorem, you are relating a line integral to a surface integral. Here you are relating a volume integral to a surface integral, where n is the outwardly drawn normal to the boundary of the domain. So this domain is a subset of the Euclidean point space. This is perhaps the most general form of Gauss theorem. So what we are going to do, instead of proving Gauss theorem, there are simple proofs actually. I saw one in a continuum mechanics book some time ago, but I don't want to divert our attention. Let us just understand it, know how to get from one statement of it to another and how to apply it. And then after we have convinced ourselves that the theorem is true. The set of tensor product applies when the field is of order 1 or higher. So if psi is a vector, for instance, you can get the grad of a vector, and you know that the grad of a vector is a tensor. You remember last time you told me that when you take grad, you promote by 1. When you take trace, you demote by 2. So remember, if something is of a first order, you take its grad, it goes to second order. If something is of first 0 order, you take the grad, it goes to first order, and so on. So so the tensor product applies when the field is of order 1 or higher. That is vectors, second and higher order tensors. That is when this tensor product becomes useful. When you are talking about a scalar, this degenerates to simply a multiplication. So if what we are talking about here is a scalar, the grad still appears because you can take the grad of a scalar. When you take the grad of a scalar, class, tell me, when you take the grad of a scalar, what do you get? I want to be sure that the members of this class are awake. When you take the grad of a scalar, what do you get? I want to be sure people are awake. Take the grad of a scalar, what do you get? Okay, people are telling me you get a vector. So let us say psi is a vector, is a scalar. So this side of the equation, you are integrating a vector, you are doing the volume integral of a vector. But this quantity itself is a scalar. Then what you have here, what you have on the left is a vector, but what you have on the right, what is what you have on the right? What will it be if psi is a vector, is a scalar? If psi is a scalar, the left-hand side is a vector because of the grad. On the other side, can you tell me what do you have on the right? Is it a vector or a scalar? If psi is a scalar, if we take this as just a simple multiplication, What is this quantity then? This integral on the right. The integral on the right, what will it be? Oluwa Femisire, are you answering the second question? Or which one? I'm talking now of the right-hand side. What is the right-hand side if xi is a scalar? If xi is a scalar, what will be the right-hand side? Are you still there, class? Admin, is the class still alive? Admin? Nsika Kepo. Nsika Kepo said you should get a fourth order tensor. Wow. Definitely. You are telling me that if xi is a scalar, the right-hand side will be a fourth order tensor. Why will it be a fourth order tensor? No. Israel said it's a vector. Tulu Olope said it's a vector. Oluwa Tomiwa says vector. Oluwa Tobi Chidera vector. Binejesu vector. James vector. But because it's simply then a vector multiplied by a scalar multiplied by a vector, the scaling of a vector. No, you are wrong. It's not a scalar. It is a vector because this n here is a unit vector, and this is the vector area. N the s is the vector of the area. The area vector, this is the scalar, and then this is the direction. So if you multiply that by a scalar, then what you have is a vector. So Daniel, you are not correct. It's a vector. Okay, so you can see that if the left-hand side, if the function itself is a scalar, it's a scalar field, this becomes a vector equation. If it is a vector field, this becomes a second-order tensor equation. If it is a second-order tensor field, this becomes a third-order tensor equation. It doesn't matter. So this form of the statement is very simple, easy to remember, and very general. And what we are going to do, we are going to derive the simple cases. We are going to assume this thing is a scalar, and then we'll write the equation, which is what you are likely to see in your textbooks. We will derive that now from here. Then we will now go further and say, okay, xi is a vector, and we'll derive it. And then we say xi is a tensor. That is how we will expend our energy. Instead of going to prove the thing, we take a generalized format, and we obtain the ones you will see in your textbooks from there. This generalized form, I saw it in a book by Ogden. It is nonlinear elastic solids is the name of the book. It's an advanced book, so I'm not recommending you to go and read it at this stage. But that is the most general form of Gauss divergence theorem. So, but what we are going to do for the rest of the class, before we look at the examples that are prepared for you, what we're going to do is that we're going to derive, we're now going to assume that xi is a scalar, but before that, let us start with we shall now derive several more familiar statements of this theorem from the above equation. Replacing the tensor with a vector field F. Instead of xi, let us say we are dealing with a vector field F and taking the trace of both sides. So if it's a vector field F, instead of grad xi, we have grad F, and then instead of xi circle times n, we have F circle times n. Now, if we take the trace of both sides, you will remember that the trace of grad is called divergence. So if you take the trace of a grad, you get the divergence. And then you take the trace of a tensor product, you replace that tensor product with a dot. So this is what happens when you replace the xi with a vector, and you take the trace of the equation. When you take the trace of the equation, what you have here now is that the divergence of f dv is equal to f dot n ds, stating that the integral of the divergence of a vector field over the volume equals the integral of the surface. Is equals the integral over the surface of the same function with the outwardly drawn normal n, which is the usual form of the Gauss theorem. Now, many textbooks that you are going to read, when they get to Gauss theorem, this is what they are going to give to you, this equation. But what we have showed here is that there is actually a more general Gauss theorem, And that is actually derived from that general Gauss theorem. So this is the Gauss theorem for vectors. So that is the Gauss theorem for vectors. So if you have a vector function, it tells you that the divergence of that taken on a volume integral is the same thing as the surface integral of the dot product of the function with the normal, with the outwardly drawn normal. That is the vector field of the divergence theorem. So while I do not charge you with proving Gauss theorem, I expect you to be able to get from here to here. You can see that it's just 2 steps. 2 steps, very easy to move from there to here, just 2 steps. It's not hard at all. So the next thing to do is to move from this vector expression to a scalar expression. We are going to write the Gauss theorem. We are going to write the Gauss theorem in terms of scalars. And the result we are going to get may surprise you. So be careful. Be careful. It may not look like this when the function we are dealing with is a scalar. And in order to get this result for a scalar, we are going to just play a simple trick. The simple trick is that we are going to assume there's a scalar field, phi, a scalar field, and a constant vector A. If there's a scalar field and a constant vector, if you multiply the two, because you are multiplying a scalar by a vector, so what you get is a vector. So if you have phi times A, that's a simple times, because multiplication by a scalar is a simple thing. It's a straightforward thing. There is no ambiguity in multiplying a vector by a scalar. It is multiplying a vector by a vector that you need to tell us what product you are having in mind. If you are multiplying a vector by a vector, you have to tell us, is it a scalar product, is it a vector product, or is it a tensor product? But if you are multiplying a scalar by a vector, there is only one interpretation, that is called scalar multiplication. So when you do scalar multiplication of phi A is now a vector. So you can use phi A to replace F in this expression. The expression on page 52. Instead of F now, we are going to have phi A, where phi is a scalar and A is a constant vector. If that is the case, just that substitution, we have that the divergence of F, which is now phi A, is written as integral of phi A dot n ds. Now, because A is a constant vector, by our hypothesis, we are hypothesizing that we have a scalar field and a constant vector. By our hypothesis, A is constant. So we can take A dot out of this integral and say A dot of this integral. So because, and it is, we can take a constant in and out of an integral. Any constant can be pushed in or pushed out of an integral with no consequences. Now, what about the left-hand side? The left-hand side, we remember that if you take grad, you have to remember the comma operator. You see, you have a phi AI, comma J, EI, circle times EJ. We did a lot of this last lecture. If that is the case, you remember that the comma is like now the differentiation of a product. The differentiation of a product, one of the things in the product is a scalar, the other one is the scalar component I. So when you do that, you are multiplying, you are differentiating a product. So you can differentiate phi and leave A alone, and then you can differentiate A and leave phi alone. So that is the thing. But if you differentiate A, remember that A is a constant, you are going to get 0. So because A is a constant, so only one of those terms survive. That is when you differentiate phi and leave A alone. Because if you differentiate A and leave phi alone, the answer you get is 0. So even though there are supposed to be 2 terms here, you are only going to get 1 term. So if you look at that, and you can now say, if you take the trace of what we have on this equation now, you take the trace of it, you have A phi comma J EI dot EJ, which is simply A dot grad phi. So that is that. So So for an arbitrary constant vector, we have that divergence of phi A is equal to A dot grad dv, which is A dot phi n ds. Or you can see that since there's A dotting on both sides, since we are having A dot on both sides, we can therefore say that grad of phi dv is equal to phi n ds, which is this is the scalar form of that this is the scalar form of that thing. And let us go back again. Remember that what we want is the divergence of phi A, which is the trace of the grad of phi A. You take the grad of phi A, you get this. Take the trace, you get this. So on both sides, you have A dot and A dot. So if A dot this is equal to A dot this, we assume that the thing they are dotting should be equal. So that means that grad of a scalar field, dv, is equal to integral over the surface of phi n ds. So this is the Gauss divergence theorem for a scalar field. So there are the other result is a tensor field. I want to omit this because it's not of immediate value to us. Of a second order tensor, it's not of immediate value to us. Let us just leave that one. So what I want you to remember is the general formula from which we can extract the divergence theorem for all sizes of objects, whether they are scalars or they are vectors or they are tensors or they are higher order stuff. Everything is contained in this formula here, which I don't know who invented it, but I saw it in the book by Ogden. So that is that. From there, you can get the result for a vector field. From there, you can get the result for a scalar field. And from there, you can get the result for a tensor field and for higher quantities. Let's see what the time is now. The time is 6:01. So we have less than 30 minutes left. In the time we have left, I'm going to show you what I've been busy doing in the past few days. In the past few days, I've been trying to populate your database with new questions based on the things you have learned since last week. And just want to show you so that you can prepare for your, there should be a test either next week or the week after. But as soon as the platform is ready for self-test, you should be doing your self-testing. So if you have enough self-tests, there will be no need for any class test. So if I have enough reports of your self-test, then that's okay. So I'm already populating the database with some questions. I just want to show you some of the sample of the questions that are going into your database. So when I show you a question here, notice that it is actually a question you can meet in your test or exam. So it is not because it is a subset of whatever is in the database that you are going to see. And even when you don't see the question directly, there will be, for every question I show you, there may be 20 such questions with just changing the figures, but whereas the skill that you learned in solving this particular question would put you in a good shape to work other things. So just bear that in mind. So take the first one. I call this domain examples. Say for a cone with vertex at origin, axis along the y-axis, vertical height h, and included angle theta. The position vector at a typical point on its curved surface is A, B, C, D, or E. So I want you to go into your, please, when you are answering this question in the chat, type 5105. That is the code. That is the code for this question. And type A, B, C, or D, or E. And let me see what you think is the correct answer. And I want to see whether it's something you understand to do. So up to the chat room and answer the question based on what we learned last week and today. We're looking at the position vector on the typical point on the curved surface of a cone. This cone has its axis on x-axis and its vertex at the origin. I've seen two answers. I'm not making comments yet. Please, Sajuwon and other people, type the number of the question you are answering so that we will not mix it, because I'm going to supply you more questions. Please, before you go on, before others answer, you cannot just simply guess the answer to this question. Let me give you a hint. Everybody that has answered so far got it wrong. Everybody. All the answers that you have gotten so far is in error. Don't guess. It's not something you can get by guesswork. Okay, then. Ubara. Okay, then. You said none of it is correct. Is that what you think? One of the answers is correct, obviously. James Udotong is the first one that has gotten the correct answer. The answer is A. The answer is A. Surprising that H does not even appear in the answer. The answer is A. On the curved surface, the answer is A on the curved surface. And well, please go work that out. And if you keep having difficulty in understanding that, that is a question. That question is already in it's already in your questions database. And Israel Anifalaje. It is 5105, not 51015. Okay, type the correct question and answer. Okay, everybody's getting it now that I've said it, but please make sure you work it out. Work this thing out and do a sketch to see that that is the correct answer, not the one. Of course, if I gave it to you, if the axis are lying along the z-axis, you will quickly get the answer. But I can change the axis, and so you should be ready for the axis to be changed to another direction, and then you should still be able to understand, because the way to get it is still the same. Okay, so I'm going to move to the next question. Please always write the number of questions you are answering so that there's no mistake. Okay, the next question is the position vector at a typical point on its base. We are now talking of the base. Now, in this case, the cone has a vertex at origin, and the thing is the axis is directed along the negative z-axis, vertical height h, and including angle theta. So we are now looking at the position vector on the base of the cone. On the base of the cone. On the base of the cone. Okay, I'm not going to give you the answer yet. I want to go to the next question. I will go back over it. Okay, 5113. Identify the surface parameterized as the position vector xi plus yj plus the square root of s squared plus y squared cot theta k. That is 5113. The A answer here is missing some details. It should be axis along the z-axis, the axis along z. That's the question A, answer A. Axis along z. Okay, I'm going to move to the next question. 5117. For the conical surface represented parametrically by the position vector xiyj plus the square root of s squared plus y squared cot k, a vector parallel to the x-axis s. How do you get the vector parallel to the x-axis? How do you get the vector parallel to the x-axis in 5117? You know the position vector here is a function of x and y. How do you now get the vector parallel to the x-axis? Differentiate. James Udotong. You said differentiate with respect to what? When you are looking for the vector parallel to the x-axis, differentiate with respect to what? Yes, with respect to x. Okay, so what is the correct answer? There's no dot product here. It is just differentiate with respect to the x-axis. James, we don't talk, yes, you got it right because you already know what to do. So what this question is doing is expecting you to remember that in order to get the vector, the tangent vector parallel to the x-axis, you have to differentiate with respect to x. And when you finish differentiating with respect to x, you will choose the right answer. You cannot choose the right answer by guessing. You choose the right answer by differentiating with respect to x. And please be careful to observe the unit vectors that are relevant in these situations. The unit vectors that are relevant are shown, so be careful to recognize them. Okay, I'm going to repeat, I'm going to go over the questions again, but before I do that, let me just take you to what I think might be the last one. Okay, let us look at the last one. The last one, for the conical surface represented parametrically by the position vector rho e rho phi, emphasizing the constancy of the half included angle. Given that E rho theta phi is sine theta cos phi and blah blah blah, and E theta phi is cos theta cos phi and so on, and then E phi theta phi is minus sine phi cos I cos phi j. A surface vector tangent to the theta direction is. First of all, before you answer the question, I want you to I want you to first of all look at the question and tell me whether there is any contradiction. And on the second line, I said I used E rho as function of phi. On the third line, I use E rho as function of theta and phi. Is there a contradiction there? If there is a contradiction, say so. If there is no contradiction, explain why there is a contradiction or why there is no contradiction before you answer the question. Because understanding that may actually help you to be able to pick the correct way to know how to answer the question. Is there a contradiction? Let us discuss this. After that, I will go over all the others. I will go back again because these I've already displayed the 5 questions that I want us to take a look at. But please, class, coming to the exam with an attitude of guessing the answer is the way to fail. You will not likely get the right things just by coming to guess. I'm waiting for somebody to comment on the fact that I gave 2 functional values for E rho. Why, Oluwafemi? Why is it not a contradiction? No, the reason why it's not a contradiction is not because they are this vector. There's a reason why it's not a contradiction. There's a different reason. But why? Rho contains phi infinity. No, rho does not contain phi. Rho and phi are different variables. They do not contain it. They do not contain each other. The position vector rho E rho is the magnitude, E rho is the unit vector. So there is no problem there. It is important that you know why there is no contradiction here. Because in the one case, I express E rho as a function of phi. In the other case, I express E rho as a function of theta and phi. Because they are nonlinear, wrong. Munyoluwa, you are just guessing. No, it has nothing to do with linear independence. Okay. Since nobody is, okay, the third equation, E phi, not E theta phi. And it is E theta phi, and you will see why both of them are right. It depends on the context. Yes, that is Oluwatomiwa Ikudife. Along the surface of a cone, theta is constant. Remember, we are looking at the conical surface. Along the conical surface, the constancy of theta is already emphasized. Once you are if you look at, let us go back again. Let us go back to let me just show you a picture of the, let me just show you a picture of a cone. look at the picture of a cone here. Can't you see that the angle theta here, which is pi over 4, is constant everywhere along the surface of the cone? Whereas in general, E rho contains theta in general. But when you are constrained on the surface of a cone, theta is constant for the surface of a cone only, just on the surface of a cone. And the question here is on the surface of the cone. That's why before the question, even at the beginning of the question, I said for the conical surface represented parametrically by the position vector, emphasizing the constancy of the included angle. For the cone, for the conical surface, is the source of surface of the cone. That is where it is constant. So this second one is generally speaking, E rho is generally speaking a function of theta and phi. But on the surface of the cone is a function of phi only. So these three equations are the general equations for E rho, E theta, and E phi. But on the surface of the cone, this E rho, phi is the correct thing. There's no contradiction there, as long as you are limited to the surface of the cone. So I hope that is, so now answer the question. The vector tangent to the theta direction is what? What's the vector tangent to the theta direction? Okay, let me tell you a trick. In all the questions that I've posted, the answer to every question is A. I didn't want to tell you that in the beginning. So, of all my questions, the answer to everyone is A. Won't it be nice if that is how they will appear in your test, that all the answers will be A? Won't it be a very nice thing? Do you want me to make it like that so that in the objective test, all the answers are A, so that you just pick A, and get 100%? Would that not be nice? I don't know, you don't want that. I thought you want, that's that Olajide is talking. Very nice. Okay, but let me tell you what happens is that when I populate the database, this is how I write it. So the computer program scrambles it and it knows where it has put the correct answer. So that's what happens. So when I'm typing it in, everything, I always type the correct answer as A. But when it enters the program, then everything is scrambled. Even me that I set it up, I never know what A, B, C, D, or E value will have a correct answer. I don't know it. I will not know. So, and when two people are even given the same question, it will be a different scramble. So you might be answering the same question, and what is A for somebody can be not necessarily be A for the other person. So that's why it is. But just for you to notice, as I typed it out to your notes today, every correct answer is in A. And the question on the question number 5113, I did not complete the sentence for so it should have been the curved surface of a cone with vertex at the origin, axis along the z-axis, included half angle theta, and included half angle theta. So that is what should have been there. But at least I hope you have an idea now of what I'm asking. Remember that all these questions are on the cone. When I sit down again, I will ask questions on the sphere, and I'll ask questions for other kinds of surfaces. But the idea is the same. What am I testing? I'm testing whether you can parameterize the unit vector so that it lies on the surface. 2, I am testing whether you remember that to get a surface tangent is to differentiate according to that particular variable. 3, that to get a surface area, you differentiate to 2 parameters and you take the cross product. Those are the things that we have learned through this time, and we are able to test them. And you will be seeing the office is already populating the database with these questions and more. I just picked 5 out of 21 that I put into the database over the weekend. And once I'm free a little bit, I'm going to put more. Please, the previous video on the LMS website is not downloaded. I hope admin, can you, Ike Okoro's poor English is there. But despite the fact that he didn't pass his English, you can still help him. Can you? Or should we penalize him for that and not answer him?
I give him time.
Admin, please, do you see what Ike Okoro
Yes,
said?
I saw what he...
Please forgive him for the poor English. English is not his native language, so it's not his fault. Okay. So say you can solve that problem, can you?
Yes, sir.
Okay. Okay. Ike Okoro has repented. He has corrected himself. Okay. So that's where we are going to leave it today. By next week, I should have by next lecture, which is on Wednesday. I think our lecture is on Wednesday. Next lecture, I should be able to give you examples on what do you call it? On things like the Green's theorem, Stokes theorem, some more examples. The way they will appear on your platform. So be getting ready to see them. But I hope the examples you have seen shows you how to prepare for your test. So please don't just guess and pick what is looking nice, because it may be wrong. Okay. So, ladies and gentlemen, I think we have reached the point of drawing the curtain today. It's already 6:26. We have only 4 minutes to go. If there is any question, please go to your chat room. Please obey the instructions, and wish you all the best as you go. So we'll see you on Wednesday.